Hi everybody, Dr. Pingle here. Welcome to part one of spatial interpolation. Today we're going to be covering some of the theoretical underpinnings of spatial interpolation, as well as some of the tools involved with gridding data. This is a pretty useful topic. Many of you may have been exposed to part of this in your previous GIS courses, but we're going to dig in a little bit deeper. And this is going to be part one of a three-part series on spatial interpolation. So I'm going to start out with a story. When I was a kid, I was really into reptiles. That's probably true for at least some of you. I would collect snakes. I had a couple of lizards. My favorite thing in the world was to sort of check out library books and read those and sort of see where all of the reptiles were. And the book that I had actually would have these little maps in them, and it would sort of outline where the different snakes and lizards and whatnot would be. And I grew up in eastern Iowa, so a little town kind of right over here. When I would look at these books, I would sort of look carefully to see if that line overlapped with where I was. And so the most dangerous animal nearby was the timber rattlesnake. And so I would hear stories about whether, that someone had seen a timber rattlesnake kind of back in the woods. I kind of lived in a rural area next to a timber. And, when we would go hiking or walking around back there, we'd always be on the lookout for these timber rattlesnakes. And I never saw one, but it was a pretty good time looking around for them. So this is the range of the timber rattlesnake. And I would just sort of look and look and look to see if those were where I lived. The attribution on Wikipedia for that particular map where I pulled this from is the IUCN red list, which is a really nice little data set that describes where these endangered species are, threatened species, I should say. And so you can go to that website and you can look for whatever you like. And I would encourage you to, if you've got a second, pause the video and just take a look at this website. One of the things that you can do is you can browse these different species and look at the ranges. And you can actually download the data if you create an account. So I've done that. And I brought that into ArcGIS and overlaid them. And so I could really kind of zoom in a way that I couldn't have done when I was 9 years old, and just sort of look very carefully. Is the timber rattlesnake range in Ely, Iowa? Definitely it is. And after that, I moved to DeKalb, Illinois, and you can see that we're just a little bit short there. The idea is, could I have gone 16 miles southwest to get and see some of these snakes? Obviously not. That's not the way that this works, despite my 9-year-old self's disappointment. I bring this story up as a classic example of a problem in GIS where the way that we record spatial data, points, lines, and polygons is often a poor representation of the way that these phenomena often exist, right? One of the problems, and I've mentioned this frequently, is that sort of, you take your first GIS class and you learn about points, lines, and polygons, and before you know it, you're thinking about everything in terms of points, lines, and polygons, and you forget that that's an abstraction. And in some cases, models reality very, very poorly. And so species distribution maps are a really good example where polygons don't work very well at all. Right? What we have, even if we had a perfect set of geospatial data where we had radio tagged every timber rattlesnake in the United States and we could track its movements at all time, how would we draw that map? Would we draw it around the furthest snake that we see? Would we want to do it differently? Maybe polygons aren't the right way of solving this problem at all. So not only when you're kind of reflecting on these kinds of analysis problems, you have to sort of really kind of get back to what's the real underlying reality of the phenomena we're trying to model, and how do we operationalize, or how do we accommodate this digitally? How do we turn those things into a map that we can use? And it gets worse than redlining. So redlining is a term that is an old term. We'll talk about that here in a second. But just sort of drawing lines on a map is sort of the how I'm using it here. And that's not the only way that we can kind of make mistakes in terms of representing the geographic phenomena that we're interested in. This is another example. This is crocodilians per country. It's a choropleth map, and lots of things are wrong with this picture. So just take a second to kind of take a look at that and see how you feel about it. What isn't right about what you see here? So feel free to pause the video and think about that for a second. So if you ask me what's wrong with this, I could tell you a couple things. One is this isn't the geovisualization class, but you could make a pretty good case for saying that this isn't a really great color ramp. It's not intuitive. You can use it, but it's not so easy. We're mixing a category of 4 to 6 for some reason that doesn't necessarily make a lot of sense. But more importantly, what we're doing is we're representing point-based phenomena by administrative boundary, which is not at all the right way to do that, right? So we generally want to try to avoid using administrative boundaries in cases where the phenomena that we're interested in don't line up well with that, and certainly crocodilian species don't respect administrative boundaries. So maybe there are better ways of representing this kind of data. Redlining, by the way, is an old practice of denying or charging more for particular services in areas. So this was a case where African Americans would be sort of denied loans or charged an exorbitant amount in terms of interest based on where bankers would draw a line on a map. And if you were on one side, you were sort of in maybe a white neighborhood and things were good, and on the other side, you weren't, on things where loans were not easy to get. So this is kind of an old example of GIS and sort of worth mentioning, at least if you haven't heard of that. If you're interested in this, there's I don't want to get into it too much in this lecture, but it's a fascinating historical topic. I'm providing a link for you here. A quick Google search of redlining in history will certainly provide you with some more examples of this. This is one really good article, by the way, from CityLab. If you've got a minute, I really suggest pause the video and at least read this text. You can follow up with that link if you find this interesting and want to pursue it a little bit further. So kind of getting back to the species map issue, what do we say about what kind of problems do we run into? This is kind of one example, redlining king mackerel, so species of fish. This is where they are. That's denoted by sort of a dark red color. Not certain is kind of a dashed line. Those don't really show up super well on the map. Certainly, this is not a fantastic way of representing this, right? Because the fish clearly don't respect those boundaries at all. It's better than using administrative boundaries, so that's a plus. But again, probably better. There are better ways of doing that, and that's kind of what this lecture is about. So I mentioned before this example of like if you could radio tag all of the timber rattlesnakes in the United States, could you? What kind of a map would you make out of that? That's not realistic. There are some really interesting cases of where they've tried to sort of tag a lot of one kind of animal, usually a relatively rare animal within a geographic range. So there's a project that I'm really interested in where they've done that with the wolves, and you can sort of track both individual wolves and packs as they kind of move around. It's a really interesting way of doing that. But that kind of information can be very hard. And just to sort of provide an example of what this might look like, you could use websites like this one, which are going to provide particular point-based observations of certain kinds of animals. So plants and insects and fungus and wildlife in general, lots of things people are interested in sort of building distribution maps out of. And this is an example of volunteer geographic information, VGI, very hot topic in geography within the last decade. Technology has made it easier than ever for people to supply this information. And sort of a good classic example of this is sort of the Audubon Society every year puts on sort of a bird watch event where people go out and count the birds, and this would be another kind of older example of that. One of the problems with VGI in general, and in this particular data set specifically, there aren't necessarily a lot of observations, and so until your VGI reaches a sort of a critical mass, it's often so unreliable that it's not really worth using. And so in this case, this is a map that I saw of the Texas horned lizard, famously found, apparently according to this database, only in Florida, which is certainly not true. This is really only a result of the problem with who has participated in this data set. That data actually comes more than just in state level data. So this is an example of looking at that same data set by county. You can start to see a little bit better resolution. That doesn't improve the quality of the data set, but at least you can sort of get a finer view of what you see. And in fact, note the symbolization here, which is good and how they're representing this. The green is species reported, and white is no data. So if you don't find a Texas horned lizard, that doesn't mean it wasn't there, it just means you didn't find it. So you can only really kind of report a positive result. You can't really report a negative result. You can actually drill into this data set even further and look at the point data if you're interested. This is an Esri map and sort of has this nice aggregation method. As you zoom in, those dots spread out a little bit. And really nicely, you can download that data. So despite the fact that this data is a little bit thin, it really is a fantastic data set. They're sort of offering you 3 different good views of the data combined with the ability to look at the data in spreadsheet form and download it. It's really a fantastic site, and hopefully more people kind of contribute to it, and it just gets better and better as the years go on. So one naive way to solve the problem of something like a species density map, and we'll look at how that compares to other kinds of examples here in a second, would be to just put a dot down wherever we saw one of those things. And that's not a terrible idea for exploratory data analysis. This is EDA is kind of a big topic. The way that you explore your data and visualize your data where you're trying to learn what it says is different than the way you explore it, or the way that you sort of create visualizations for public consumption. So just putting a single dot down wherever you saw thing A or thing B works fine when there are only a few dots, but when we get to a lot more dots, that method doesn't work so well. This is an example of what can happen there. So this is what happens when we have too many dots. These are high priority 911 calls in Baltimore. This is a public database that you can access. These were pulled down sometime in 2019. You can download the updated data sets if you're interested. But it's very difficult to get a sense of the density of dots, right? They start to crowd each other, and one dot is kind of placed on top of the other dots. And that means that it's difficult to get a sense of the overall spatial pattern. It's not impossible. You can start to see where there are no dots, right? So these kind of green areas show up as not having a lot of dots, rightly or wrongly. That could certainly be an artifact of how the data were collected. But even so, you can start to see thinner areas and denser areas, and yet it's still hard to sort of make good judgments once it reaches a certain level of density. So most of this kind of interior part of the city looks of a similar density, and it would be nice to be able to sort of tease out those differences. I got to use my marker here. So this area seems very similar in nature, right? But if we visualize this differently, we'll be able to see that more clearly. This problem is far from unique in geography, so data visualization and transformation is integral to many aspects of science and engineering. This problem of sort of how do we compress very large amounts of data into something like an aggregate is quite common. Within most of statistics, this is a pretty old problem, and so a couple of kinds of visualizations have been invented to sort of do exactly this. If I'm teaching a class of 1,000 people and I want to look at the grade distribution, I don't just want to look at a list of those. It's going to be hard for me to make sense of that raw data. Neither do I want to make just put a dot down wherever I see an observation. It's going to be hard to, I could put a dot down on a number line wherever that number was, but those dots too are going to start to pile one on top of the other. So things like histograms and box plots were invented to help us aggregate and see patterns in groups of data, in large amounts of data where we can't really inspect individual values. And the histogram is really exactly what we do with a choropleth map, right? So in one sense, we are drawing a vertical line, a vertical bar, I should say, to whatever the frequency value is here. And in the other, we shade that administrative region based on the number of something within that region. Oh, yes. Take a moment. It's not a geovisualization class, but do take a moment to kind of take a look at that legend and see why maybe that, what could be done to improve that. There are variations on the equal interval histogram. So within choropleth mapping, we talk about different kinds of ways of aggregating the data. We can have equal frequency, where each class has the same number of cases in it. We can have equal interval, where the class spans are the same size, so 0 to 10, 10 to 20, 20 to 30, and so on, and other variations as well. Histograms are, interestingly, basically equal interval kinds of representations. And so if you wanted something like equal frequency, you can do that within histogram. They look pretty strange, but that's not really that much different. It's just sort of a play on exactly what we do when we do equal frequency groupings in choropleth mapping. This is the same data visualized with 10 and 20 bins respectively. We've taken a look at that already in some other cases here. So specifying the bin or the width of the histogram size can really change the overall appearance and add a lot of value up to a point. So if we made this 2,000 bins, then the bins would be too small to be very useful. And finding that sweet spot, there are ways of sort of making good guesses about what that sweet spot should be. But usually you can just sort of trial and error your way into a reasonable representation. This is a 2D scatter plot, so this should be familiar to most of you by this point. We've looked at Jupyter Notebooks for this, so I would take a moment to look at that code and make sure you understand what it's doing. But this is essentially what we had done way back in Notebooks 1 and 2. Now, this starts to bring us back a little bit. That's a bit of a diversion into statistical representation, statistical grouping. How does that apply to geography? Well, if you think back to those 911 calls, they're essentially just a cluster of dots on a map. And what we want to do is we want to bin those up and represent those. And one way to do that is with a 2D histogram. So within the Python universe, we can use matplotlib and we can use the function hist2d to create these kind of representations. It's a very easy way of doing it. And here we're calculating out we're letting the computer sort of figure out what kind of bin sizes and whatnot it should use. Now, what I want you to do here for just a second is compare the scatter plot that you see at the top to the 2D histogram that you're seeing at the bottom. Those are representing the same data. But how do they look the same and how do they look different? Do you feel like the bottom is sort of a faithful reproduction? Keep in mind that if I had been a little bit more careful in the construction of this figure, I would have made sure that the bounds, the x, y bounds were exactly the same in these two images. So do be aware that on the x scale, we go from -3 to 4 on the top, and we go from -2 to 3 on the bottom. So we're trimming things out a little bit. But even so, most of you can sort of match dots from one to the other, are the high spots where you would have put high spots. If you were asked to sort of identify the top 3 clusters on the scatter plot above, would you have circled the same clusters as are sort of visible by the red colors and orange color in the 2D histogram representation below? So returning back to sort of a geographic example, Baltimore, like many municipalities, is publishing a lot of their data online. This is a really nice, sort of aspect of modern life. You know, cities have gotten wise that it's nice to be able to publish this data. Lots of research and lots of benefits can come from sharing the data easily in this way. You can imagine that sharing crime data isn't exactly what cities want to do, but there are many benefits to being open about your data, and I think many cities have finally realized that. So if you're interested in where the data for this part of the lecture came from, this is the source, but I will post the data set along with, I will post the data set directly to the course webpage here so that you can download and work with this data too if you're interested. This is an example of the 911 call list. It's a really big CSV file that contains information about addresses, and it contains latitudes and longitudes. So this is a very easy way of working with this data. You'll notice, though, by looking at the raw data that you download, that it's not the friendliest data in the world. So we have a line at the top for record ID, the call date and time, the priority, the district, the description, the call number, the incident location as an address, and the location which includes a latitude and longitude. But take a quick look at the incident location and the location. We've got some replication of information here. So we've got on the top example, 400 Winston Avenue. And then the second column, or the column after that, I should say, is 400 Winston Avenue, Baltimore, Maryland. And then on a new line, 39, the geographic coordinates, right? So the latitude and the longitude, in that order, which again is important to keep track of. That data is put out daily. The entire record has over 4 million rows, and it's probably more than that because I downloaded this data sometime last year. So this is a really nice data set and very useful for the examples over the next couple of lectures. One of the things that you'll notice is that if you try to bring this data in, it doesn't contain the latitude and longitude. That original data, again, is fairly badly formatted. Not all of the information is making it into the location field. And so as a result, we can't do something simple like we'd like and use the display XY data. We have to work a little bit harder at it. So I'm including a Jupyter Notebook that uses Pandas to fix the field. I would encourage you to take a quick look at that and sort of see how it works. It's not a strict requirement, but you may be interested to see how you can use some of the tools you've mastered so far to do a very simple data repair, something that would actually be pretty tricky to do directly sort of with classic buttons and whatnot in ARC, but it's relatively easy to do with something like Pandas without ever actually really needing to interact with a GIS proper, right? All of this is really just it's just data, and it doesn't need a geospatial data set or a geospatial data package to process it. You can do this stuff directly with Pandas. You don't even need GeoPandas to do this work. So a highly useful tool set that you've been working with. So this particular example, it fixes the field, which I'll show you here in a second. That's not in this part. But we only read in the first 10,000 rows. That's a handy thing to be able to do. When data sets get really big, you don't necessarily want to read in the whole thing. You might only want to read in specific columns, or you might only want to read in 100 rows. Work with the data a little bit in kind of a small way. Write the code that you need to process it, and only then start working with the whole data set, right? So remember that a really convenient way of doing this work is to work with the smallest amount of data that really represents the problem that you're working on, and then scale it upwards after you've figured that part out. There are still some errors, calls that came from well outside the central region. The final cleaned and projected data set is posted online. So if you want to sort of jump ahead of the line and sort of see how this stuff worked, that's the data set that you're going to want to work with. The tool that we would usually use to start processing data like this is featured a raster. That creates a raster of specified cell size according to a field input. So basically you specify the geospatial layer that you're working with, in this case the Baltimore 911 data. I want to look at the priority. So you can see that this is high, medium, non-emergency, low. We've got a number of different values here. The output raster, which is what I want it to be, and then the output cell size. So it will calculate an output cell size for you if you don't supply one, but it's often good form to set that to something reasonable, in the same way that ArcGIS will generate legends with sort of ridiculous amounts of precision, too many decimal points. It's often, or the classification routines break things up in really weird ways. It's often good to keep this pretty human readable, and so I would encourage you to specify output cell sizes that make sense for the problem that you're working with. So 50 meters, 100 meters, whatever makes sense for the problem that you're working on, make that the output cell size. This is what that output looks like, just as an example. These are the high priority calls, medium, non-emergency, low, and emergency. I will grant you that the color schemes are not fantastic here. That's okay. If we were publishing this, we would definitely want to attend to those a little bit better. Pretty much about as bad of a color scheme as you could get. But this is what was default assigned, and we'll roll with it because this isn't really what we want anyway. You can kind of squint and look for patterns. Do you see patterns in this data that you didn't see with the point data? Maybe, maybe not. Probably one of the things that you can. Well, we'll hold off on that for a second because we have slides that sort of talk about that directly. So featured a raster. This is a really useful tool. This is one that I would really recommend you kind of keep in your back pocket anytime you're going to want to deal with big data, lots of points that you need to sort of make sense of and aggregate. This is going to be probably your first go-to tool set. This is going to do much of what you want to do, and we'll talk about more advanced ways of doing that with kernel density tools and whatnot, applying sort of buffers to these points. But this is essentially recreating a two-dimensional histogram. If you run into problems with featured raster, keep in mind also that there are specific toolkits for doing this task for particular types. So there's a specific point to raster tool, there's a polyline to raster tool, and a polygon to raster tool. Those are very useful, and if you know the data type that you're working with, which I suppose you always will, consider jumping to those rather than just using feature to raster. But even feature to raster is a pretty good start. So more specialized tools are basically going to let you do more different kinds of things. That's going to start to get really useful. So this is an example of what those options look like. This is essentially a version of what we just saw. So we're using an input feature. In this case, we were looking at bus routes. But of the optional parameters here, one of them is the cell assignment type, which turns out to be a very key parameter. You can see right now that that's set to most frequent. We'll talk about that momentarily. And again, a priority field and a cell size. That cell size is often really important. So that cell assignment type, essentially what we're doing is we're sort of counting the number. Well, we have a number of dots within a pixel, right? So for the 911 stuff in Baltimore, let's assume we wanted to make some pretty big pixel sizes, let's say 1 kilometer. Lots of points are going to fall within a single kilometer. how do we want to aggregate those? We can do a number of different things with those depending on what the data is and depending on what our purpose is. One very likely thing that we would want to do is count them. So just how many points were there in the given cell. And I would say that probably for most of you, that's going to be a very common thing that you're going to want to do is just count them. But you can do other sort of things with them. You can add up all of the values. If we wanted to, if each dot sort of had a number associated with it, if you think back to species distribution, maybe, at this one point we saw 5 timber rattlesnakes, and at that point we saw 2 timber rattlesnakes. We could use those values in the data set and add those together so that we could get a better picture of individuals rather than just counting dots. We might take the mean. So in our 911 data, our call urgency might have a value associated with it. Let's say it's on a scale from 1 to 5, 1 being the least urgent and 5 being the most urgent. We could potentially report the average urgency value of all of the points within them. And so other things you might be interested in, standard deviation, maximum, minimum, the range, those are probably going to be used less often, but it's just as easy to calculate those things. So do keep in mind those different things. We haven't talked about most frequent. That's what we had applied on the last data set. So we had these different kinds of 911 calls. Maybe we just want to say, like, if 9 of them were of an urgency level 5 and 3 of them were an urgency level 2 and 1 of them was an urgency level 1, we could ask, like, what's the most common value there? And that can sometimes be really instructive. It's a bit of a stretch to think why we would need that for 911 data, which is actually why I chose that. I wanted to show an example where the fit for cell assignment type was not good, to get you thinking a little bit about how you might want to declare that when you use this particular tool. So that, in combination with the value field, which is the second from the top, will control what happens when you see more than one point in a cell, which is very common. And so if you do want to count things or take the mean, you need to specify the mean of what field or what column. And so that's what's done in the second option there, value field. And so my advice is you should really understand the implications of using all of these. All of these are going to have a time or a place in which they are the best fit for the job. I would say that the most common is count, but mean is going to be fairly common, and even most frequent value is also going to be pretty common. So do be aware that this is a very settable calculation. So going back to our 911 data, this is an example of sort of what we saw before. We don't really know how multiple points per pixel were handled. Was it the first value that it saw? Was it the last value? Was it the most common? So this is an example of where we're being a little bit more particular. Instead of using the feature to raster, we're using point to raster. That lets us be a little bit more thorough about how we're defining these things. You can see that I've adjusted the cell size to be a more appropriate value. Again, this is just done by eye. There's really no right or wrong answer here, but I've set the cell size to 500 meters, which visually seems like it matches pretty well with what we're looking at. And then we're classifying these according to the most frequent type of priority call within that little pixel or grid square. You can see that most of these then are a medium. You can see the high values are brown, and you can see the low values are red. And we also have non-emergency in here as well. So that gives you a very different picture about where are most of the calls high priority calls, where are most of the calls low priority calls, and it looks pretty random, which is probably good. I had a student of mine a few years ago create a poster that I liked quite a bit using this. So he had downloaded crime data for LA and New York City and created a map essentially of which crimes were the most common at different places. So you can see that in New York, which is an interesting view. New York City is a lot more compact compared to LA. So the cell size was kept the same between both of these, but because LA is such a sprawling city, it's not quite as good of a visualization. But the New York one turned out really good. The larceny theft you can see is quite common. You can see where burglary is common. You can see where grand theft auto. There are a couple of pixels of that. It's an interesting way of kind of breaking down the data. So this is an example of taking our 911 data and using point to raster using count as the cell assignment type. So here we're just saying how many 911 calls were there within a given pixel. This starts to give us sort of another view of where 911 calls are happening. We can see high concentrations and medium concentrations and low concentrations. So this is an easy way of sort of dealing with that dots are stacked onto one another problem. We can really start to look at the hotspots this way. One of the things to keep in mind is that when you're working with this stuff, you do want to make sure that it's projected properly. That's a good thing to keep in mind every time you're working with spatial data. Always ask yourself whether the projection that you're working in is appropriate. ArcPro has some nice improvements on this stuff, even ahead of ArcGIS Desktop. More of the operations are conducted in sort of a geographically appropriate way. Even so, you really should take the time to project your data in a way that makes sense. So if you're working with the 911 data, I think it was distributed as latitudes and longitudes, which you can assume is WGS 84. Don't just run your calculations on that. First of all, your units are going to be in degrees, and angular measurements don't make sense to that many people. What is 5 city blocks as a fraction of a decimal degree? Good luck figuring that out. Whereas if you do this and you make your units in terms of meters, it's a lot easier to think about how big is 100 meters, how big is 500 meters, than to think about what is 0.15 of a degree. That's even sort of setting aside the issue that 1 degree of latitude is not equal to 1 degree of longitude, which is a separate problem. And certainly inflicts a lot of downstream trouble at the mid-latitudes. If you happen to be working with lat-long data at the equator, you don't have to worry about that so much. But if you're at the mid-latitudes, it's an absolutely essential problem. Always make sure that your data is projected before you start working with it. Keep in mind that there's a difference between the project tool, which projects from one projection to another, or one coordinate system to another. There's a difference between project and define projection. You use define projection when you're missing your projection entirely, which can happen a lot of times. If you download this data as CSV, you may need to define it as WGS 84 before you get started projecting it into something else. And so these project and reproject and define projection, they can all, they're all interrelated, and they all have particular purposes, and it pays to sort of think carefully when you're using those tools. If you're working locally, you can project into state plane or UTM. UTM is good if you're sort of working with global data sets. Oftentimes, if you're working with data in the United States, it can be more useful to use the state plane coordinate system. One of the reasons for this is because a lot of the ways that road networks and whatnot have been set up in the United States, they're all basically tuned to that local state plane coordinate system. And so when I want to make a road that runs directly east-west or north-south, I'm going to build that road on matching it to state plane coordinate system and not UTM. The upshot to that is that those two coordinate systems don't align perfectly. If you think back to maybe your first maps and mapping class, you may remember that there's a difference between true north and grid north and magnetic north, although the magnetic north part doesn't really bother us here. But grid north and true north are not necessarily likely to be the same either. And so if you project into UTM, you may find that your map looks a little bit tilted when it shouldn't be. So keep that in mind as you start working with these local data sets. It's just one thing to be very careful of. So we're going to wrap up there with this lecture. I wanted to thank you for your attention. I hope this was a good introduction to the spatial interpolation problem. We've got 2 more lectures to go. Thanks very much for listening, and we'll see you next time.